Good afternoon, everyone. My name is Mihir Ganwani. I'm a third year student at Pilani Hyderabad campus. Today I'll be presenting about the design and investigation of MEMS-based thermopile detector arrays for infrared sensing applications. In today's world, IR sensors are being used from smartphone to space to defense. So we worked upon to optimize the development of IR sensor that uses thermocouple working on different aspects such as size, material to make the sensor more sensitive and efficient. Our study pioneers advancement and contributing to IR sensor technology. So what are the application of IR sensors? IR sensor is being used in the night vision radiation thermometer that was effectively being used in the corona period, IR imaging devices and infrared tracking that the missile system uses to lock on the target. So on what effect the IR sensor is working? The thermocouple main effect that it works on is the Seebeck effect. Here we can see the illustration that it has two material 1 and material 2, that are two different thermoelectric material. And when we create a temperature difference at two of the junctions, we get a potential difference that we can describe as V is equals to N alpha delta T, where delta T is the temperature difference, alpha is the Seebeck coefficient, and N is the number of thermocouple connected in series. After that, what are the advantage of the thermopile sensor that we are using? First of all, it helps us measurement of the moving object. That is the main plus point. It is smaller in size. It is affordable cost. Large output voltage due to the multiple thermocouple that we attached in the series. And also it is non-contact. So after we have done with the advantages, we moved on to creating a basic thermocouple design. So first of all, we created a single layer thermocouple structure that had a P-type structure, N-type polysilicon stripe connected in series with the help of aluminum stripe. So what here we did was we created a hot and cold junction for getting improved sensing and heat transfer. After we were done with the single layer thermocouple structure, we dwelled upon creating a double layer thermocouple structure that was already created, but we tried to optimize the structure that was created. So in this structure, what we did was we used an P-type. We created two layers. In the first layer, what we did was we placed an P-type. Above it, we placed an SiO2 spacer to insulate the heat. Above the SiO2, we placed an N-type. This was our layer 1. For the layer 2, what we did was we placed an N-type over which we placed an SiO2 and then again P-type. So we had P, then N, then P. So what we did was the top layer had P and N-type. So we connected this layer using a aluminum stripe. And for the layer 1 that we connected, we used the climbing aluminum structure that you can see over there to connect the vertical layer. After we are done with the double layer thermocouple structure, we tried to optimize it more and try different geometries that could be used to get more advanced sensitive thermocouple. So we came up with the stacked double layer structure. Stacked double layer structure was inspired from the double layer structure that we created. So the only difference here was we increased the number of thermocouple that we were using in the same area that we had used previously. So in this case, what we did was we used a P-type block over which we placed an SiO2 spacer, then again an N-type block, then SiO2, then P-type, then SiO2, and then N-type again for the layer 1. And we connected the vertical layer using the climbing aluminum structure. And for the layer 2, what we did was we had an N-type structure, then SiO2, then P-type, then SiO2, then P-type, then again SiO2, and then over which we had a P-type. So here we made a series of PN and connected in the series, and from the top we again made a series of N and P, and then it continued till the bottom. So we had P and PN till the bottom. This was our main focus of study that we did to get an enhanced sensitivity. So this was a structure that was performing well compared with the single layer and the double layer thermocouple structure because we had more number of thermocouple in the same area. So what was the analytical model that we came up with? To check our results, whether we were getting the similar results from the simulation theoretically, we backtracked the Seebeck coefficient by calculating. First of all, we used a basic thermocouple design, single layer thermocouple design. We calculated the heat transfer from the equation of Q is equals to KWP by L and the temperature difference. After we were done with the heat transfer equation, we calculated the middle temperature of both the stripes, and then we analyzed the T average of this. And then we determine the Seebeck coefficient using the, as we from the simulation we already knew the voltage that was being created. So using the T average and the voltage we knew, we calculated the Seebeck coefficient and then we compared it with the Seebeck coefficient that we were using for the simulation purposes. After we were done with the analytical model, we then focused on the silicon dioxide layer thickness that should be used to get the voltage that increase thermocouple voltage. So when we tried with the different thickness of the values, the trend was such that when we decrease the thickness, the voltage difference was higher, and when we kept on increasing the thickness, the voltage difference kept on decreasing. Because this is the reason for this was, as we increase the length of the silicon dioxide, the heat radiation increased more and it led to the reduced heat transfer from one end to other end. After we are done with the silicon dioxide layer, then we focused on the optimizing the value of the P and N stripes that we are using to create the thermocouple. For this, we did the same simulation. We first started with the 2 micrometer, then went on with 1 micrometer, 0.5 micrometer, and 0.25 micrometer. We saw a similar trend that we had in silicon dioxide. As we kept on decreasing the thickness, the voltage kept on increasing. When we analyzed the length of the thermocouple stripe, it was not playing that major role as the thickness was playing in increasing the voltage. So after we were done with the thickness part, we went on analyzing what can be the best material that should be used to develop the thermocouple structure. So we had different thermoelectric materials in our mind, such as gallium nitride, silicon, polysilicon, bismuth telluride. But we rejected the gallium nitride because it had a high thermal conductivity, which was not suitable for our model. So we kept our model simulation with bismuth telluride and polysilicon. In this, what we did was we created a single layer thermopile that had a 10 thermocouple structure connected in a linear fashion. And we created a hot junction that was kept at 500 Kelvin and the cold junction that was kept at the room temperature. And we did the simulation on this for single layer structure. Similarly, keeping the same environment as we have kept with the single layer thermocouple and kept keeping the thermocouple's geometry same as a 10 layer double layer structure, we did the simulations. After we moved on to doing the same simulation, keeping the same environment, same geometry of the array with a stacked double layer thermocouple structure. And here we use the aluminum as aluminum because it was efficient as an interconnect for efficient heat dissipation between the layers. So after we are done with the simulation purposes, here we can see with the result that bismuth telluride was outperforming polysilicon in every layer, rather it be single, rather it be double, or rather it be a stacked double layer. Also, you can see a trend was forming when we see the voltage output of polysilicon single layer structure, it was 0.6. It gets double in polysilicon double layer, that is 1.2. Here we can also say that our simulation that like in single layer we were using only 2 thermocouple, but in double layer in the same area we had used 4 thermocouple. Theoretically, the voltage should double. Here we can see that the voltage gets double, and similar case with the stacked polysilicon. The voltage gets double, but the somewhat efficiency is lost during stacking the double layer. That's why we didn't kept on increasing the vertical layer. We stopped at the stacked double layer. So what are the conclusions that we can make from this? We can say that if we are diminishing the SI2 layer or N/P type block strip enhances the output voltage, and stacked double layer bismuth telluride thermopile exhibits significantly elevated output voltage as compared with other polysilicon or double layer or single layer thermocouple structure. Why does bismuth telluride outperforms polysilicon? Bismuth telluride outperforms polysilicon due to its exceptional characteristics such as narrow band gap and high carrier mobility that it has, and also it has a superior Seebeck coefficient compared with the polysilicon and a low thermal conductivity. So the reference that we used for the study. Thank you so much.